stay on, and I'm going to make sure that you can get your labs uploaded since they were giving you a hard time. So last week we did the electrical conductivity lab, where you guys used the little device attached to the 9-volt battery and figured out if something was a good conductor or a weak conductor. So you did a fantastic job on that. Either of you have any questions about the lab you did last week? Ashley, I did not grade yours yet because it'll be much easier for me just to enter the grade in Moodle, so we're going to do that after class. But Amy, I did do yours, and you did not answer the questions in your results. So what you can do if you want is you can go ahead and redo that. Just don't do the whole lab again. Just go ahead and redo those results, the questions 1 and 2 on page 25 of your lab book, and I'll update your grade for you. Okay, it's not a big deal. I just wanted to make sure that you could go ahead and update it and resubmit it, and I will update your grade. Okay, so there is a chance to fix that. So like I said, this is week 3 of chemistry. I'm guessing everyone who's coming would be here by now. So we are going to go ahead and just get started. I'm going to release a PowerPoint for you. And today we are going to talk about phase changes, or when matter changes phases. This is probably something that is very familiar to you guys already. If you put an ice cube out on your counter, it's going to melt. That is a phase change. When you boil water, the water is changing from a liquid water to a gas through evaporation. So let's go ahead and take a look at this PowerPoint. Now it starts with something called a phase change diagram. This may or may not be something that you have seen before. A phase change diagram is something that is very important to chemists and most scientists. Now when you look at this graph, there are 2 important points. The first thing is the y-axis. It has temperature, and it starts low temperature and goes up. And across the x-axis is heat energy. It starts at a low heat energy and goes up as you travel to the right. Now our phase change is going to start as a solid. If we look below our diagram, or below the line on the graph, that's what happens as the temperature and heat energy increase. So we start as a solid. As it warms up, it's called melting, and it melts or becomes a liquid. As a liquid warms up, it boils, and as a gas warms up, and as the liquid warms up again, it becomes a gas. Now if we look above our phase change diagram line, we see what happens when it is cooling. The opposite. So as a gas cools, it condenses and becomes a liquid. As the liquid cools, it freezes and becomes a solid. That's the basic phase change diagram. Today, we are going to do a lab that has to do with melting points of some different objects. We're going to look at water. Okay, water is a great example of what we can use for the phase change diagram because it's something that's familiar to all of us, something that we use every day in our lives. So water exists on our planet in 3 states: ice, water, and water vapor. So what causes water to be in one phase or another? What do you think? What causes water to be in one phase or another? Just go ahead on and turn your mics on and answer that one.
like the temperature of like where it is or the heat energy around it?
Great job, Ashley. So if you look so you can see my camera again, so you make that PowerPoint small. I have a glass of water right here. It's water because of the temperature in the room that I'm sitting in. Now, if I was in a freezer and I had the water in there for a long enough time, I would be dressed differently, and this would be an ice cube. If I was in a sauna and had this water on a heat, it would be boiling up and be water vapor. So the main reason that something is in the phase that it's in is the temperature of its environment, the temperature of the air around it, or the temperature of, if you're warming it up, the heat source underneath it. So let's talk about energy. When energy is added to a substance, the energy causes the particles in the substance to move faster and be farther apart. So the energy, there's more energy in a gas. The particles or the molecules are moving quicker than the particles in a solid. Okay, if you look at the diagram on the right here, the particles in a solid don't have anywhere to go. They're so tightly packed. The particles in a gas have lots of places to go. There's lots of room for them to move. So what happens to the particles when energy is taken away from the substance? So let's think about water as our example. If we have water and we take energy away, so we are taking the heat energy out, so we're cooling it, what happens to that water? Either one of you, go ahead and answer that.
It becomes a solid because all the energies. Is that what you're asking? Sorry.
Awesome. It becomes a solid because the energy is leaving it, it's becoming colder, and it becomes a solid. Perfect. So energy content is responsible for the different phases of matter. Matter can be made to change phase when energy is added or taken away from the substance. It goes both ways. Water can become ice, ice can become water. Either way. So melting is when something changes from a solid to a liquid. Melting is the changing of a solid to a liquid when the substance absorbs heat. Melting point of a couple of objects you are familiar with. The melting point of water is 0 degrees centigrade. The melting point of table salt is 801 degrees centigrade. And the melting point of a diamond is 3,700 degrees centigrade. That's a wide range. Freezing is when something turns from a liquid to a solid. It's the opposite of melting. Liquid changing to a solid is freezing. Freezing occurs when the substance loses heat energy. The freezing point of a substance is equal to the melting point of a substance. And this is just that graph again, except this time I just put the little particles and the space between the particles in it. So now vaporization is when a liquid changes to a gas. So vaporization is the changing of a liquid to a gas when the substance absorbs heat energy. Vaporization occurring at the surface of a liquid is called evaporation. When you boil water in a pot, the water right at the surface is becoming a gas. It is evaporating. Evaporation is a cooling process. As water in the perspiration evaporates from your skin, it absorbs and carries away heat energy from your body. It's letting your body or enabling your body to lose energy. It's enabling the water as you're boiling it to lose energy as well. If enough heat energy is applied to a substance, particles inside the liquid can change to gas. These particles travel to the surface of the liquid and then into the air. This process is called boiling. Okay, and this is the same diagram we're going back to again, and it's just to show you that kind of the second plateau is where this boiling takes place. So the boiling point is the temperature at which a substance will boil. For water, that temperature is 100 degrees centigrade. For table salt, that temperature is 1,413 degrees centigrade. And for diamond, that temperature is 4,200 degrees centigrade. So what is the difference between evaporation and boiling? Anyone want to make a guess?
Sorry. Boiling is basically the jump from, I'm confusing myself. Evaporation is where the water is turning to a gas because it's on the surface, and boiling is basically just the water just being heated up and it's just starting to reach that point, I guess.
That's a perfect explanation. The evaporation is the water actually becoming the gas, and boiling is the process that the water goes through while it's being heated up. Okay, so that is a perfect explanation. So here's this phase change graph again, but I used water as an example. So we have ice as the solid, where if you look at the particles of the ice, they form nice little hexagons. They're nice, compact, solid, not moving. Then when it goes up and it's a liquid and it's water, you see the particles moving. You see the hydrogens and the oxygen. And then as water vapor again, you can see the hydrogens and the oxygen floating around in space. Now something different about this diagram than the phase change diagrams we've seen to this point is that on the left-hand side on our y-axis, there are actual temperatures. So we can see at what temperature water becomes water vapor. At what temperature does water become ice? You can see the actual temperatures. So when you're looking at a specific element, material, compound, whatever you're looking at, when you're looking at a specific example, your phase change diagram can include those temperatures. If you're looking at generalizations, then we leave those temperatures off and we just use it as from decreasing to increasing temperature. So now condensation is when gas changes to a liquid. So gases can change phase also in a gas to liquid phase change. A substance in the gas phase that loses heat will change to a liquid. This is called condensation. Now, how many of you have ever held a glass of something very cold? The condensation forms on the outside of your glass. That's a phase change. Water vapor in the surrounding air loses heat energy when it comes in contact with the cold glass. Water vapor condenses and becomes liquid drops of water. And again, I just put this diagram in there. It's important for us to look at. Sublimation is when a solid changes to a gas. The solid to gas phase change occurs when the surface particles of a solid change directly into a gas? You may notice this in the cold winter with snow. The snow doesn't melt, but it just slowly disappears. Or dry ice is another example that goes directly from solid carbon dioxide to gas. Okay, if you've ever had dry ice, it's kind of fun to watch. If you put it in a bowl, it will just turn into the gas. You never will have any liquid at the bottom of your bowl. It will just be gone. This is another way to look at and think about changes in phases. Okay, so take a second and look at this. The blue arrows show when heat is taken in. So as a solid becomes a liquid, heat is taken in. As a liquid becomes a gas, heat is taken in. And a solid can also become a gas. Okay, now the exact words for the solid to a liquid are right here. Solid to a liquid is melting. A liquid to a solid is freezing. A gas to a liquid is condensation. A liquid to a gas is evaporation. So let's take a look and try a question here. When Okay, go ahead and answer the poll that I just sent out. When a liquid changes to a gas, what is it called? Just choose one of the options. Awesome. When a liquid changes to a gas, it is called evaporation. Good job. All right, now let's take a look. And let's try this one. When heat is taken in from a liquid, what phase is formed? Awesome, great job. Good job, you guys seem to get this. So everything that I was just talking about when I was giving you guys examples, I was using the temperature Celsius. Now, when scientists are talking scientifically, most of them use either Celsius or Kelvin. When we are talking in the US, most of us would use Fahrenheit. So for example, right now, when I was getting my kids ready for the day today, the temperature was supposed to be 65 out. It was 65 Fahrenheit. When I told them that, they kind of had an idea of what they should put on. They both put on long pants and a short sleeve shirt. Now if I had told them, well, the temperature is going to be 100 degrees Celsius out, They would have looked at me like I had 10 heads and had no idea what I was talking about. So we need to convert when we are using science. And when you are talking and writing your lab reports, you should be using Celsius. So here's a little comparison for us. So the boiling point of water is 212 degrees Fahrenheit, 100 degrees Celsius, or 373 degrees Kelvin. Kelvin is another scientific form of temperature. Melting point of water is 32 degrees Fahrenheit, 0 degrees Celsius, or 273 degrees Kelvin. And the freezing point of water is 32 degrees Celsius, 0 degrees Kelvin, or 273 degrees Kelvin. And if you look at absolute zero, that's when the Kelvin scale is at 0. So that means the Celsius is negative 273 degrees Celsius and negative 459 degrees Celsius. Go ahead, Ethan. Make sure when you talk, you hit the green talk button on the bottom of your screen. I wasn't able to hear you. So let's go ahead and just check to make sure that your microphone is reading the right microphone. So if you look at your screen right now, the bottom left-hand side, you should see a wrench. Click on that wrench. Click on Microphone Setup. You should have another pop-up box that shows up. I have to choose Logitech headset for my headset to work. So go ahead and choose whichever microphone you are trying to use. And then click OK or save whichever it is. Click OK again. And go ahead and try your microphone again. No, I don't think your microphone is working. So you can go ahead and type something in the text chat if you would like. Hit the send and I can answer whatever question it is that you have. Okay, so here, okay, so let's see. Can anyone else hear me? Go ahead and answer the poll if you can hear me or not. Ethan's saying he's having trouble hearing me. Okay, Ashley can. Savannah can. Okay, I think it's a connection with Ethan, so I've asked him to log out and log back in. While we're waiting for him, let's take a look at this diagram. Now, we're not going to add anything here, but what I am going to do is we are going to take this picture and put it on our whiteboard, and we will label it there. So, maybe not. Oh, it doesn't seem to want to let me do that either. So we're going to look at the diagram, and we're just going to verbo through it. So what would I call it as it goes, a gas goes from steam to water. From steam to water. Go ahead and raise your hand or put it in the text chat. Go ahead, Amy.
From steam to water, it's called a condensation.
Awesome. Great job. All right. How about if it goes from water to steam? Water to steam. Go ahead, Ashley.
Evaporation.
Awesome. Well, I think you guys definitely have this under control, so we are going to go ahead and get to our lab for the day. Today, our lab is on page 19 of your lab books. Now, part of your assignment is to make sure that you have read the labs before each class to make sure that we have no issues. So I am going to assume that you all have read the lab beforehand. Now, if you have read the lab, you know that we need to have some boiling water. I am going to go ahead and go over to my stove right now. I'm going to start my water boiling. It says we are only going to need the 50 milliliters. I'm going to go ahead and do more than that, so it's ready and all set. 50 milliliters is not enough to actually boil on my stove. So if you could go ahead and go get your water started boiling so we can go ahead and set the lab up. We're going to do that. I will be right back on screen in a minute. Okay. Once you are back from your water being set up, go ahead and click yes, just so I know everyone is back and paying attention and ready to move on. All right, fantastic. Now what we are going to do is make sure our glasses are on. Okay, now I had mentioned last week that I was hoping to get some volunteers to show us their labs on camera, and that everyone was going to have to do it at one point. So is there anyone who would like to volunteer to let us watch them do the lab today? You're not going to have to do any sort of explaining. You're not going to have to talk. You're just going to share your video with us. Now I know for some of you it's super early and you may be still in your pajamas. Does anyone want to share their video this week and kind of get it over with? No volunteers? All right, then you'll get to watch me again this week, and I will be emailing one of you this week during the week to let you know that you are our camera star next week. So we are doing lab number 2, melting points and supercooling. The objectives for today's lab are to measure the melting points of 2 organic compounds and observe the supercooling of a liquid. Now, as we go through today's lab, remember, boiling water is hot. It will burn you. Okay, other than that, there is no real safety issues. Obviously, if you get any of the chemical on your hands or in your eyes, you should go wash it off immediately. There should be no issue with the eyes because you have your gorgeous goggles on. But if you do get anything on your hands, just go wash them off in the water. If you get stuck and you have a question, please make sure you go ahead and ask. So how we are going to get started today is we're going to go to page 20, and we are going to go to number 1, scoop a small amount of cetyl alcohol into a capillary tube. So you should have your cetyl alcohol out. And your capillary tubes are the very small tubes. Your cetyl alcohol actually is in a little tiny Ziploc along with your palmitic acid. It's in a little white container. That's your cetyl alcohol. Your capillary tubes are wrapped up in the blue cloth in your lab kit. They are very, very fine. If you bang them too hard, you will break them. They look like very small test tubes. One end has an opening, the other end does not. You are going to scoop a small amount of cetyl alcohol into the capillary tube. Now I'm going to angle my camera, and I would like you to watch me do this before you attempt it. To do so, you're going to open your cetyl alcohol. You're going to take the open end of your capillary tube, push it in. Now if you look, I have a little bit in my capillary tube. I'm going to slowly bang it, gently, and the cetyl alcohol is falling down into my capillary tube. You want to have several millimeters of the sample in the bottom of your capillary tube. So I am going to get some more. That's not enough. To get more, I'm going to dip in and repeat the process all over again. Oops, and I dropped it. Okay, now I believe I have enough, and I'll hold my blue cloth so you can hopefully see. That should be plenty of cetyl alcohol. Okay, you can lay it flat. It is not going to fall out of your test tube. There should be a couple of millimeters. So if you want, your lab kit also has a ruler in it. I think if you have 2 to 3 millimeters in there, that should be plenty. You can take your ruler out. And here. If you look at mine, the white, I have about 5 millimeters in mine, or half a centimeter. That should be more than enough. So once you have your acetyl alcohol, okay, once you have your acetyl alcohol in, go ahead and click yes. Just so I know we are all still together. Since this is the first time you guys are using your capillary tubes, I would expect that it's going to take you longer than it takes me. So take your time, do not rush. Okay, take your time. Make sure you just keep an ear out for your water so that it doesn't burn because you didn't put enough water in it. I can hear mine boiling, but it is fine because I know I put enough water in it that it is not going to run out of water. And where is my water? Okay, so now you have that. Now we are going to get our thermometer. Now, you are going to take your thermometer you are going to attach it to your capillary tube using an elastic band. There are elastic bands in your lab kit, and your thermometer should be in your lab kit. Now my thermometer actually broke on me when I was testing this, so I'm just going to show you how to attach it using a wooden stick. You're going to take your capillary tube, put it at the bottom bulb of your thermometer. You're going to take the elastic and go like this. You're going to try not to drop your thermometer like I did yesterday. So here is what you have. Except instead of a wooden stick, you will have a thermometer. That is how you do step 3. Now we are going to get our water for step 4. So go get your boiling water for step number 4 in the 50 milliliter glass beaker. Make sure you are using the glass beaker to put the boiling water into. You are going to pour the water into the thermometer and then, you're going to pour the water into the beaker, then put your capillary tube in. Make sure no water gets into that tube. The sample is going to be clear. Once you are done with step 5, you need to stop. Okay, I'm going to go grab my water. When you finish step 5, stop. And click yes. You now should have a setup that looks like this, except yours has a thermometer, not a wooden spoon. Now I do have a different thermometer. It's just a little bit different than yours, so I did not want to try to put my capillary tube to it. So now we are going to go ahead and we are going to add water from your wash bottle to the beaker, stirring constantly. Once what's connected to the thermometer starts to turn milky white, you're going to stop adding cold water and you are going to observe the temperature. Okay? Now, you do not need to have 50 milliliters of water in this beaker. That's going to be too much. So start adding cool water, either by pouring, by putting it in your wash bottle. Yep. Hold on 1 second, Savannah. Okay. So this is what it looks like, except instead of a wooden spoon, you have a thermometer. You are going to pour cool water until the materials in the capillary tube turn white. And if it's taking a long time, you may need to get some ice water. It's going to turn a milky white. It's not going to turn dark white. Okay, mine has turned. So I am going to record my temperature in degrees Celsius right in my lab book under cetyl alcohol. Okay, and this is the freezing point of acetyl alcohol. So it's the second row in your data point. Now you are going to slowly add boiling water to the beaker, stirring it constantly. And when your sample turns clear again, that is the melting point. Okay, so go ahead and do that. Make sure you're stirring it. So the water is being mixed. And once you finish that, go ahead and click Yes. Take your time. This is not a race. Okay, we're just waiting for one more of you. Please make sure you are taking your time. It is not a race. Okay, we want everyone to get accurate results. That's what we're concerned with. Nope, we're not waiting on you, Ethan. I know you don't have your lab kit. Okay, but everyone needs to take their time. It's not a race. Okay, now what you're going to do is you are going to look at your numbers. You should have a melting point and a freezing point for acetyl alcohol. Now you are going to subtract them if there was any difference between the two. So for example, I got 49 degrees for my melting point and 44 degrees for my freezing point. So for me, my supercooling was 5 degrees Celsius. Okay, so now we are going to go ahead and you are going to do steps 1 through 7 again, except you are going to use palmitic acid instead of acetyl alcohol. So go ahead, steps 1 through 7 with palmitic acid instead of acetyl alcohol. Go ahead and take your time. Anyone want to share their camera with us? Let us see what you're doing. No? Okay, we'll go ahead and do, all right, yay! Okay, so in order to share your camera, I'm going to turn mine off. Where my camera normally is, or where my video normally is, Amy, there is a picture. It's a blank screen right now. You're going to click underneath. It says allow your video to be shared. Click there. And hopefully your video, it looks like it's loading. Oh, there you are. Yay. Perfect. Great. So as you're doing the lab, we are going to watch you. Everyone else, go ahead and continue to do your lab as well. Okay, well, you are doing a great job with the lab. Oh, water wasn't hot enough. That's fine. Go ahead and heat it up, and when you guys are finished, go ahead and click yes on the screen. Amy's going to heat up her water again and give it another shot. That's what happens sometimes. Remember to take your time. There is no rush. If you want good results, if your water needs to be heated again, go ahead and let it heat up. Don't rush. All right, we just saw Amy mixing and measuring her temperature. Okay, make sure you're taking your time. You can't rush water warming and water cooling. It needs to do it at its own speed. You just need to pay attention to the temperature. Read your thermometers carefully. All right, great job. So everyone clicked yes that they were done with the palmitic acid. Good job. Thank you for sharing your video. I'm going to go ahead and turn you off there. Awesome, thank you. And I'm going to turn me back on. Fantastic. Once your chemicals are out of your hands, you can take your beautiful glasses off. So in this lab, before I forget to tell you, the little capillary tubes are trash. The elastic bands are trash. There's enough in your lab kit that you do not need to try to wash these and save these. The beakers, wash bottle, thermometers, rinse them out with water. They only had water in them. None of them actually came in contact with the chemical. So there's no reason to rush to rinse them out right now. But when you're done with lab today, just make sure you rinse them. Let them dry before they go back into your shoebox. But the capillary tubes are not worth cleaning. Throw them away. Trash, in the trash can. If you want the rubber bands, Ethan, you certainly can keep them. But there are enough in here that you will not need to reuse rubber bands. So now for the cetyl alcohol and the for the cetyl alcohol, you subtracted the numbers to find your supercooling, if any. You are going to do the same for your palmitic acid. And in your labs, you are going to make sure that in the results section, you include your data, as well as answer questions 1, 2, and 3. So we can kind of compare our data with each other. What I would like to do is I'm going to turn on all of your whiteboards. And Ethan, I know you don't have your lab and weren't able to do the lab, but the rest of us are going to just put our supercooling numbers up here. So let's see. We are going to have Mrs. Berg, Ashley. Oh, sorry, I missed the L there, Ashley. Amy and Savannah. Okay, we're each going to have our own line. I don't need all of your results up here, but I would like you just to go ahead and include your supercooling for the cetyl alcohol, so cetyl, and the palmitic acid. So go ahead and put your number up in the appropriate box. Remember to write on our whiteboard. You can either hit the blue or the big black A and then tap it on the screen, or you can use the pencil and write. Now, we are not all going to have the same results. I do not expect us to all have the same results. I want to see your results. If you notice, I did not just put a number up here, because when we are doing science, whether it be chemistry, biology, physics, a number means nothing. The number needs to have its units. In this case, the units are degrees Celsius. Okay, so go ahead and put your data up here so we can compare. There are no wrong or right answers. My guess is if you were to complete this lab again, your answers would be different. The more you complete a lab, the more times you complete a certain task, the better your results are. Which is why scientists often do multiple trials of their experiments to make sure that they are getting good results. Okay, so for the most part, our numbers were pretty good. Savannah's cetyl alcohol and Ashley's palmitic acid, those are pretty big. But those were your results. You can't change what you get. That's the results I want to see in your lab report. And if you look at question number 1, it says the published melting points of cetyl alcohol and palmitic acid are 49 degrees Celsius and 64 degrees Celsius respectively. Do your results agree? Mine are pretty close. What would cause your results to differ? So let's say maybe Savannah, I'm just going to pick on you for this one. Maybe Savannah's result was 59 for cetyl alcohol. What I want her to do is think about what might have caused her results to be off. Maybe could she have read her thermometer wrong? Could the water have not been boiling? Could the water not have been cold enough? Could the temperature not have gone down enough? Maybe was her sample not at the bottom of the thermometer? Think about what you did. My suggestion to all of you is when you are doing your lab report this week, do it today, tomorrow, maybe Wednesday. Don't wait until next Sunday because you're not going to remember what you did today, next Sunday, as clearly as you do right now. Now, what I want to do is I found a really neat video on supercooling where there is someone who, through trial and error, supercools water. So I would like you guys to go ahead and watch this. Now, when we watch a video in class, I think we did it last week, but just to remind everybody, if you look at your whiteboard screen, which is where you should be right now, there are 3 icons across that top purple toolbar. You are going to click the third one that says Applications. I am going to release something to you called supercooled water. You're going to click on supercooled water. The video is going to come up. You may have to watch an ad for 15 seconds. Once you can go ahead, skip ahead through the ad, and go ahead and watch the video. Okay, so we're going to take a couple minutes and go ahead and watch this video. Okay, well, you all should be back from that now. I thought that was a neat little experiment showing supercooled water, something that we don't have time to do in class, something you certainly could try at home. So we did an experiment on melting points, freezing points, and you saw a supercooled water experiment. So that was just a little fun thing that I wanted to show you guys. Now, what I do also want to do is I had told you that the last couple minutes of each class I wanted to look at a fun chemistry topic if we had time, and it looks like we do have time today. Before we go ahead and look at this, does anybody have any questions about either the lab we did today, the lab we did last week, or anything else that we have talked about? Go ahead, Ethan.
What does the gas form of metal look like?
Not sure I understand your question. It's a gas form of a metal, meaning like the gas, I mean, it would be like a gas in the air, like a gas form of iron? Go ahead, ask, what exactly are you asking?
Like after it's molten but still keeps getting superheated enough to become gases, what would it look like? Would it just look like this gray blob that's floating? Like, is it possible to get something like that? Like gas metal?
Oh, hold on. Sorry. I'm not sure, you know, like everything can exist in each phase of matter, but in order for like iron or diamond to be a gas, it has to be at such a high temperature and pressure that it's not really possible for it to happen on Earth, for it to vaporize and become a gaseous state. I'll look into that and see, to be honest, if there are any metals that could happen and in like under normal circumstances be a gas on Earth. So I'll look into that and get back to you next week. I honestly do not know, other that they are not normally in a gaseous state, not normally found in a gaseous state on Earth. So that kind of probably doesn't answer it at all, but I'll look into that one for you. So your homework is to write up this lab report. I'm going to show you guys a brief little video about fireworks right now for kind of our chemistry of the week topic. And Ashley wanted to stay on so I could show her how to upload Moodle assignments. If you are having trouble uploading your Moodle assignments, you are more than welcome to go ahead and stay on as well. But first, let's watch this firework video. And once the video is over, you do not need to come back to class. I hope you guys have a great week, and I will see you next Monday. We do have class next week, even though it is Columbus Day. All right, enjoy your week.